Today we will cover the topic of logical reasoning. Actually, in our lives, we use logical reasoning at every point of time. Every action that we do is based on some kind of logical reasoning. For example, when we go out, we see cloud in the sky and we take an umbrella along, very day-to-day activity. But behind that also there is logical reasoning. And over course of history, various logical reasonings have been used, but philosophers have identified that these logical reasonings can be categorized into two types: inductive logic and deductive logic. So, there are two types: inductive and deductive. Inductive is where we go from a particular situation to a general situation. So, it is like particular to general, and this is general to particular to particular. For example, when we go out and we see cloud in the sky, we take an umbrella. On what basis are we taking this decision? It is that from our childhood we have repeatedly seen when there is cloud in the sky, it may rain. And by observing particular instances of this event, we have made a general inference that if there is cloud in the sky, then it may rain. This is a typical inductive logic, typical example of inductive logic, where we go from particular to general. Through particular observations, we come to some kind of a general conclusion. On a particular day, when we see cloud in the sky, we take umbrella along because we argue that if there is cloud in the sky, it may rain. Today, a particular day, there is cloud in the sky, so it may rain. So, again we are going from general to the particular, an instance of the deductive reasoning. And all our reasonings are based on this kind of either deductive or inductive reasonings. All our activities are based on that. Today, let us understand inductive reasoning in a more detailed fashion. So, we are talking about inductive reasoning, inductive logic. In fact, inductive logic is at the base of all sciences. We do come to general conclusions and these become the laws in science. And how do we infer those laws? By observing particular instances. And that is why at the dawn of Renaissance, Francis Bacon insisted that the method of science should be very large scale observation of nature, natural phenomena, and then collecting the data together and then deriving general conclusions out of these using inductive logic. And much of science has actually progressed following that prescription. Now, let us look at some typical examples of inductive inferences. For example, all insects have 6 legs. This is an inductive inference. Copper turns green when dipped in vinegar. In all planets have elliptical orbits. Volcanoes are located close to plate boundaries or boundaries between tectonic plates. The first one comes from biology, second one comes from chemistry, third one comes from physics, and fourth one comes from earth sciences, geology. But notice, how did we arrive at these conclusions? All insects have 6 legs. Has anybody counted the number of legs of all possible insects? No. We have collected a few samples of insects and counted the legs, and all instances we have found the number of legs to be 6, and so we have generalized the conclusion and inferred that all insects have 6 legs. So, notice that we have actually measured the number of legs in a sample of insect populations, and we are now making a conclusion regarding the population of the all insects. And naturally, there is what is known as an inductive leap. We know this much, but we are inferring more than that. That is an inductive leap. In the second one, copper turns green when dipped in vinegar. Has anybody dipped all possible examples of copper in all possible solutions or vinegar? No. Somebody has tried a few cases where pieces of copper were dipped in vinegar and they turned green. So, then after observing these small number of cases, people came to the general conclusion that copper in general turns green when dipped in vinegar. Has anybody actually measured the orbit of all possible planets? No. When Kepler made the observation, or Kepler actually deduced the planetary orbits from Tycho Brahe's observation, actually 5 planets were known: Mercury, Venus, Mars, Jupiter and Saturn. And based on the data collected, observational data collected by Tycho Brahe, Kepler deduced that the orbit would be elliptical. So, we had only 5 examples, but based on that, scientists argued that in general the orbit of all planets would be elliptical, and Newton deduced his theory based on that general premise. He did not talk about this particular planet's orbit would be elliptical, that particular planet will be elliptical. He said his theory indicated that all possible orbits of planets will be elliptical. Similarly, in case of volcanoes, we did not really observe all possible volcanoes. People noticed that volcanoes are in general located close to the plate boundaries, and thus this conclusion came. So, what I am trying to point out is that in all cases we have observed only a small number of things, and we are inferring something that is general in nature. So, there is an inductive leap involved, and also since we are going from the known to the realm of the unknown, there is a bit of uncertainty involved. And therefore, when a scientist makes a comment regarding this, one has to take that caution. But on what basis do we justify taking that inductive leap? We are talking about the basis for inductive leap. The basis actually are two. One is called the law of uniformity of nature. It says that nature does not behave erratically. Same kind of things behave in the same ways. So, that is the law of uniformity of nature, and the second is the law of causality. So, behind every event there is a cause, and if the same causes pertain, then the same effects will follow. So, that is the law of causality. And so, based on these two premises, we conclude that it is reasonable to have that inductive leap. But it is true that we have a bit of doubt regarding inductive inferences, and so we always make statements taking into account that element of doubt. How do we say that? There are two types of inductive inferences. This can be of two types. First one is deterministic. It says that unless contrary example is found, we can state that, and then we can say, for example, we would say unless a contrary example is found, we can state that all insects have 6 legs. That means, if you keep on counting the number of legs and find an insect with say 7 legs or 5 legs, unless that happens, then we can say that all insects have 6 legs. Here I am not talking about a situation where the leg has been broken or torn, or I am not talking about that. The second is the probabilistic. What is probabilistic? In this case, we say that we can say with a high degree of confidence that this statement is true. So, we can state a high degree of confidence that the statement is true. So, this is the statement here. Now, in this case, how do we measure the confidence? Actually, it is in terms of probability. We would say that the probability that the inference is wrong is very low. So, that is the level of confidence. So, we make statements of this kind, keeping in mind there is a non-zero probability that whatever we have inferred based on larger number of observations, that will be proved to be wrong. For example, if we observe where the heart of human beings are located, it will be found to be located on the left side of the chest. And if we observe say 10,000 humans, we might find that in all 10,000 these are located on the left side of the chest. But still people have found that such humans exist with left on the right side of the chest, and therefore, the inductive inference is actually not correct. Somebody may have observed swans and may have concluded that all swans are white, because he or she has observed say 100 swans and all of them were white. but that does not mean that there cannot be any black swans. So, one has to state the statement in a taking into consideration that possibility. So, how did we come to these conclusions? We have observed a few cases. We have observed a few cases where copper was dipped in vinegar, and so based on these finite small number of observations, we conclude something. So, this is called simple enumeration. Where we conclude based on a few specific cases where we have observed something. We enumerate and say that this is what has been observed, so we generalize it. It is clear that such generalization would be doubtful because we have observed a smaller number of cases. But there may be situations where we have completed the enumeration. So, this is like complete enumeration. Where is complete enumeration? A situation where we have completed the observation of all possible instances. Say, if we say that all months in a year have the number of days less than 32. In fact, we have noticed that this is true for January, February, March, April, and we have completed all the 12 months and say then it is a complete enumeration. In general, we do not have that opportunity, but in mathematics we have. So, let me cite an example of complete enumeration in mathematics. In mathematics, there is a technique of proof called inductive proof. For example, if I want to say that show that a statement A is true for all positive integers. How do we prove it? We say, we show firstly that if A is valid for a number n, then it is also valid for n plus 1. And then we show that A is valid for say n equal to 1. So, if it is valid for n equal to 1, then it would be valid for n equal to 2. If it is valid for n equal to 2, then it will be valid for n equal to 3 and so on and so forth. So, you actually exhaust all possible numbers, and then you conclude that this is true, that a statement A is true for all positive integers, because we have completed the enumeration. So, these are cases of complete enumeration. There are situations where we do a incomplete or simple enumeration and infer something. This is a situation where it is called a improper induction. Improper induction is where it is obtained just by observation. I have observed a few cases of white swans and we conclude that all swans are white. That is just by observation. But if we somehow can obtain a causal connection, why all swans should be white, or why when a piece of copper is dipped in vinegar, why does it turn green, then it is called a proper induction. causal connection. Connection is understood. That is why working out the causality behind any event is a part of inductive reasoning. We try to obtain proper induction. But remember, all investigation starts with improper induction or something that is observed in nature in a few instances. That gives a scientist a reason for look for causality. The scientist looks for causality and finds a causal connection. When that happens, it goes to the stage of proper induction. In many cases, we need to obtain a inference regarding a number. For example, it is called a quantitative inductive logic. Where we are trying to get an estimate of a quantity. For example, if the question is what is the average weight of all possible male sparrows, adult male sparrows, then it is a quantity that we are trying to find out regarding a population, but obviously we will do the measurement on a few collected samples of adult male sparrows, and then we try to obtain something in general. So, here also we are trying to obtain a estimate of the average weight of the adult male sparrows by taking a sample. So, again we are taking a sample and we are trying to obtain a conclusion regarding population. And how to do that, we will come to that in this course, but the conclusion would be of the type that, let me write an example, the body weight of adult male sparrows lies in the range this range I am writing here, say M1 to M2, it lies in this range with probability say P, which means that we are not stating that no adult male sparrow will lie below or above this range, that we are not saying. We are saying that with some probability we can state that the adult male sparrow's body weight lies in this range. This is also an inductive inference in the sense that we have actually measured it on a sample and we are making a conclusion regarding a population. There is an inductive leap involved, but we make the statement this way. Sometimes what we are trying to measure is a fraction. For example, Gregor Mendel, he crossed a tall variety and a short variety of pea plants. In the first generation they were all tall, but in the next generation, in the second generation, he found that tall variety is 2/3 of the number and short variety is 1/3 the number. So, he was actually calculating a fraction, proportion. So, if one wants to obtain a proportion, that also has to be obtained that the proportion of tall variety and the short variety is in the range of this to this with probability this. So, this can be a measurement of a number as well as the measurement of a proportion, and then also it has to be stated in the same kind of form. How to do that? We will come to that in a later part of this course. So, this is the essence of inductive logic. So, what have we learned today? We have learned just to summarize, that inductive logic is where you obtain a measurement, an observation, whatever, on a sample, a smaller number of individual situations, observe something and then you generalize it. Say that all, something that is applicable to a population. And if we obtain that by simple observation of a few cases, we call it simple enumeration, there would be a bit of doubt. The moment you obtain some kind of a causal connection, it becomes a proper induction. We can be confident that the induction is correct. There are also situations where we make induction regarding a quantity, and there we have to state in terms of probability.